Now that takes us through all the flow processes, steady state flow processes that we have looked at. The cylinder piston arrangement is not a steady state, steady flow process, it's a closed system, so that's treated differently. Then we got a bunch of processes which are steady state. Now we look at some processes which are open systems, but they are not in steady state. So we look at filling and evacuation. So what filling means is that we have a tank, and into this, from a supply line, we are filling gas. There's a common example around us all the time that when a vehicle which has got a CNG, which is running on CNG, it has got a CNG tank in the vehicle, and the tank pressure keeps going down with use. At some point, it goes back to the filling station. At the filling station, they connect a hose or pipe to it that is fed by gas from a high pressure reservoir. So we can say that this is a high pressure reservoir there. And when this valve is opened, this gas starts going into it and starts filling up the cylinder. That means during this process, we got flow going through this, and the mass of this and the pressure inside this keeps increasing. The P in the cylinder keeps increasing, mass in the cylinder keeps increasing. So it keeps doing this to an automatic system. It senses what is the pressure inside this, adds a little more, and as soon as the pressure of this, that is the safe working pressure of the cylinder, is reached, it stops and your vehicle is filled. Then you have to go away. Now let's see what happens in this case. This is an example where we draw the system boundary, which is the space inside the cylinder, and say, well, there is one inlet taking place, but the state inside this keeps changing with time. So this is not a steady state situation at all. It is an unsteady situation. So we apply the first law. We have derived a very long equation, and we make various assumptions on that. We say that the state at which it is coming in, this is fixed and this is constant. This is state 1, and the state here keeps gradually changing. The mass conservation equation tells you that in a period of time, in delta t time, this m dot 1 into delta t is equal to the change in the mass of the system. And we can assume that there is no work being done here. Work done is 0. It is an adiabatic process. This whole thing is insulated. Q dot Cv equal to 0. No change in kinetic energy or potential energy of either the system or the moving fluid. Both are 0. And when we do that, what we will find is that this mass that went in, say a certain amount of mass, delta m in, its enthalpy H1, this is equal to the mass that got added over here. This will be, say this was evacuated initially, this will be delta mCv into UCV. Okay, that long equation that we had, if we solve it, remove things, this is what we will get, and it tells you H1 is equal to UCV. Okay, we are assuming that initially this was evacuated. And what does this tell us? If we are looking at CNG, which is methane, H1 we can say is Cp0 T1, this is equal to Cv0 TCV. It tells you that the temperature of the gas inside the control volume, TCV, this will be Cp0 by Cv0 multiplied by the temperature here. If this is ambient temperature, it means that this gas here will increase by 1.4 times the absolute value. So this becomes 1.4 into say 300, and that water becomes 420 Kelvin approximately there. So the temperature of the gas in the cylinder increases, and if you actually go there and touch the cylinder after filling is done, you'll find that it is quite hot. You can't touch it. So it has reached a high temperature, but the pressure is equal to the maximum possible pressure to which it can be filled, which was 200 bar. So you got gas at 200 bar, but temperature which is much higher. And the safety of the cylinder requires that pressure should not be exceeded. Which means that if you fill it up here and this is at a high temperature, as you go away after some time, even if you don't use the gas too much, the pressure inside will drop as the temperature reaches the ambient temperature. So instead of say about 80, 90, 100 degrees Celsius, this will then come down and the pressure will be less. But you cannot initially fill it up to more than this, hoping that after it cools down it will come to 200 bar. That is not permitted because the mechanical design of the cylinder does not permit us that. So that's what happens in a filling process there. And this is one set of problems that we tackle. The trouble is that since the state of the substance inside this changes with time, one have to be very careful that when we apply this equation, it is only for short periods of time. And the mass that is put in is also of a very small limited amount. Otherwise, technically, the type of integration that we did to get delta MCV, that cannot be done. One then has to say that, okay, I will take a small time, see what happened, then I will take that as the starting condition and see what happens after a little more filling. Then I'll take that as my starting condition and see what happens after filling. And that's how the calculation will proceed. It's a little more complicated, and so we do not do it in this beginning course. But it's important to know that this is what filling does, and there are many other cases where such things happen. We can look at the fact that if this was saturated liquid and this was evacuated, what will happen? And that's the example when your LPG cylinder goes for filling. It is initially evacuated, and then you are pumping liquefied butane into it. And you can say that, well, I'm putting in some liquefied butane. Am I actually getting liquid butane inside the cylinder at all times? I'll leave that question to you to think of. The opposite of this is evacuation or emptying. And what we do here is we are the opposite of what we have just looked at. We have a reservoir, say an air reservoir, from which we are taking in air. Almost every manufacturing unit, every factory will have some requirement of compressed air. So from a compressor, we keep filling into it and keep drawing it. So the analysis of this, if we want to do, we want to know well, what is the relation between mass flow rate and the pressure in the cylinder. We'll do the same analysis like what we just done a few minutes back. That this is our system boundary. We say that this is an open system, control volume approach, but this is not steady. So we apply the same equations and say that, look, there was certain mass here, it went out, its internal energy became its enthalpy over here because there was flow work coming in. So this enthalpy and the internal energy that was here, it will be equal, and you will start seeing a decrease in temperature as you draw out the gas. One of the problems in one of the assignments that I put is that instead of just having gas inside this or air inside this, I've given the example of the domestic LPG cylinder. And what do we actually do in the domestic LPG cylinder is that we are drawing air from the top, and of course there is a regulator sitting on top of it over there. So you are drawing off only the saturated vapor. And as we keep drawing out, this evaporates. The temperature inside this, you can do the calculation and see that temperature keeps decreasing. But fortunately, in domestic cooking, we do it so slowly that we don't see this temperature rise. Whatever temperature fell, the ambient would supply energy and it would come back to the same temperature. So we are drawing off saturated vapor, dry saturated vapor, even though in the cylinder as a whole, we had a wet state. There is liquid there, there is vapor over there. And as we keep drawing out, this level keeps going down. But if the temperature were constant, we always had the wet state at the same condition. The dryness fraction of the system kept going down. So inside supply pressure remains constant as long as there is liquid inside the cylinder. And that's the nice thing about the cylinder, and the pressure regulator is able to do its job quite nicely. Once the liquid is gone, you have dry saturated vapor, and then when you keep drawing out, there is no more liquid to evaporate, then the pressure on the cylinder begins to go down. And that's what I just mentioned, the pressure regulator then cannot do its job. So the pressure regulator is designed for the fact that butane will come out at a certain pressure, it will throttle it and produce a pressure which your LPG stove actually wants. Analysis of this proceeds exactly the same way as before, so I will not repeat it, but you can write the full equation. Again, make the similar assumptions that heat transfer is 0, work transfer is 0, kinetic potential energy changes are 0, and simplify the equation and solve it. The only difficult thing that happens in this type of problem is that if you want to figure out and say, what is the pressure after I drew out so many grams of this substance, then in the final case, you are left with something like two properties which are specific internal energy and specific volume. And knowing these two properties, the state is completely defined. But we do not have any nice property tables which tells you that if you know U and you know V, this is the way to calculate P, T, H and all the other properties. This is complicated, quite troublesome, and you have to, in some cases, do iteration, and even online programs which are there, very few, rarely, if any, give you the option that you specify U and V and it will tell you what the state is. It's not all that straightforward a calculation, but even if you get to the point where U and V are correctly identified, the state is fully known, you can say, well, at least I reach 99% of the problem has been solved, 1% is to use the property tables and get these values. So you can even get and quit it at this point. So that is one of the issues of filling and emptying.